All right, so here, as I said, if we claim that the average waiting time in a medical clinic is less than 15 minutes, what it means is that that is a claim. That is a claim. So we write the claim that so we usually write the claim in the alternative. So here we are claiming that the average waiting time is less than 15 minutes. All right. Then the opposite of this is that the average waiting time definitely is greater than or equal to 15. Okay. Now, let's go to errors that we can, let's go to the steps in formulating the null and alternative hypothesis. First of all, you must know the population parameter of interest. Are we testing hypothesis concerning an average or concerning a proportion or concerning a variance or even concerning a standard deviation? We must know that. Then the hypothesis test of interest to the researcher must be identified. So are we doing a status quo hypothesis? Are we doing a research hypothesis, or we are doing a claim? So based on that, we can state our null and state the alternative. That's if you are doing a status quo, or we can state the alternative if you are doing a research hypothesis or a claim, and based on it, you state the null. All right. Then we must then specify a range of values for the parameter that must be divided between the null and then the alternative hypothesis. Now, we can make errors when we are testing hypotheses. All right. We can make errors when we are testing hypotheses. And to understand that carefully, I'm going to give a certain scenario. Now, we all know that by standard, let's assume that the average ounce of milk in a tin of milk is, let's say, 160, and the average grams is, let's say, 160 grams of milk. So if I state a null hypothesis like this milk, the average is equal to 160, then the alternative is that the average is not equal to 160. What it means is that this null hypothesis that I have stated is true. So this is a true null hypothesis based on this standard. That is a true null hypothesis based on the standard. Okay. Now, if I state a hypothesis that null hypothesis that the average ounce of milk is not equal to, or let's say, let me even use, the average ounce of milk, the average grams, not ounce. I don't know why I'm saying ounce. So the average grams of milk is greater than 160 grams. Okay, and then the alternative is that the average is less than or equal to 160. Now, if I state a null hypothesis like this, that the average is greater than 160 grams, okay, this null hypothesis is false. It is a false null hypothesis because the status quo is that the thing is equal to 160. So if I state the hypothesis that the thing is more than 160, I have stated a false null hypothesis. All right. Now, when you state a true null hypothesis, All right, sorry for the interruption. Now, for you to state a true null hypothesis, we expect that when you do your hypothesis testing, if you state a true null hypothesis, every researcher should expect that when he does his hypothesis testing, the results will be that he will not reject the true null hypothesis. All right. Then, if you state a false null hypothesis as a researcher, you should expect that when you do your computations, that false null hypothesis will be rejected because it is false. Okay. Now, there is a problem. Therefore, there is a problem when we reject or when our computation says we should reject a true null hypothesis. And then there is another problem when our computation shows that we should fail to reject, all right, or we should accept a false null hypothesis. Then there's a problem. Because ideally, when you reject a false null hypothesis based on your statistical computations, there is no problem. And then when you accept a true null hypothesis, there is no problem. But the problem comes when your statistical computation shows that a true null hypothesis should be rejected, and then a false null hypothesis should be accepted. Then there's a problem. Now, what type of error do we commit when these things happen? Okay, so when we don't reject a true null hypothesis, we have no problem, it's correct. As in when we don't reject a true null hypothesis, there is no problem. But when we don't reject a false null hypothesis, there is an error, and that error is called type 2 error. So type 2 error is when we fail to reject a false null hypothesis. Now, when there is a false null hypothesis and we reject it, okay, it is correct. There is nothing wrong because the thing is false and then we have rejected. But then when we have a true null hypothesis and our statistical computation tells us that it should be rejected, then there's also another error called type 1 error. So in simple terms, type 1 error occurs when we reject a true null hypothesis, and type 2 error occurs when we don't reject a false null hypothesis. And rejecting or not rejecting, it is not you. It is the computation that you make that will show whether it should be rejected or it should not be rejected. So we will learn those computations as we move along. All right. Now, in hypothesis testing too, we must know what we mean by significance level, and we must know what we mean by a critical value. Now, significance level is the maximum allowable probability of committing type 1 statistical error. All right. Significance level is the maximum allowable probability of committing a type 1 error. Okay, that is a significance level. So if I'm testing a hypothesis at 5% significance level, that means that this is the maximum allowable probability that I could commit type 1 error, okay? All right. Now, the value of alpha is determined on the cost involved in committing type 1 error, all right? The value of alpha is determined by the cost involved in committing type 1 error. So if type 1 error, which is, of course, rejecting a true null hypothesis, if type 1 error is very costly, then the probability of type 1 error should be very small, all right? So for instance, I'm making hypothesis testing, and I believe that if I commit an error, it will really cost me, okay? That means that my significance level should be like something like 1% significance level. That means I am 99% sure of my, hypothesis testing. So the higher the cost of committing the error, the smaller your alpha level must be. On the other hand, the probability of making or committing type 2 error is called beta. All right, the probability of committing type 2 error is called beta, while the probability of committing type 1 error is called alpha. Okay. Now, those are the significance levels. Now, what is a critical value? A critical value to a significance level, it is the value that corresponds to a significance level that determines those test statistics that lead to rejecting the null hypothesis and those that lead to a decision not to reject. All right. So in simple terms, what this is saying is that every critical value corresponds to a certain significance level. Every critical value has a corresponding significance level. All right. Okay. Now, based on the explanations we've made, you realize that type 1 and type 2 error cannot happen at the same time. All right. Now, there is a chance that type 1 error can occur if we have stated a true null hypothesis, because type 1 error occurs when we reject a true null hypothesis. Okay. So there is a higher chance that type 1 error will occur if the null hypothesis is true. Once the null hypothesis is true, it has nothing to do with type 2 error, right? Because type 2 error is the error committed when we fail to reject a false null hypothesis. That means that there's a probability that type 2 error can occur if we have stated a false null hypothesis, right? Okay. Now, if type 1 error probability decreases, it means type 2 error probability increases because it's just the opposite side of it, okay? Now, remember that when we were doing confidence interval, this was the formula for confidence interval, all right? The confidence interval is the test statistic plus the critical value times the standard error, okay? The test statistic plus the critical value times the standard error. Remember this, we did it when we were doing hypothesis testing. Confidence interval. Okay, when we're doing confidence interval. Now, let me give a certain scenario here. All right, let me give a certain scenario here. Now, remember that when we are doing a two-tailed test, okay? Remember when we are doing a two-tailed test, which is normally done in confidence interval. Remember that a z-value of 1.96 corresponds with 95% confidence, okay? It corresponds with 95% confidence level. And the addition I'm going to make here is that it also corresponds with 5% significance level. Significance level. So whenever you have 95% confidence level, it means that the remainder is the 5% significance level. In other words, if I have 90% confidence level, the significance level will be 10% significance level. And I've already explained what a significance level is, all right? Now, remember that if I am constructing a confidence interval where the mean is, let's say, 10, all right? Then the standard error is, let's say, 5. All right, what it will mean is that it will be mean plus or minus the z times the standard error. All right, and this will give me 10 plus or minus 1.96, okay? 10 plus or minus 1.96 times the standard error of 5. All right, so if you multiply 1.96 by 5, if you multiply 1.96 by 5. That would be 9.8. So it will be 10 plus or minus 9.8. And this will be 10 minus 9.8 up until 10 plus 9.8. So this will give us 0.2 up until 19.8. All right. 0.2 up until 19.8. So if I'm going to draw a diagram for this, it will look like this. So the mean is 0.2 here. And then the upper limit is the mean is 19.8, all right? 19.8. So this is how it's going to be. So it means that once you do your test and the value falls in this range, okay, we are saying that it's x plus or minus 9.8. And that gives this whole range. So it means that once you do your computation and the figure falls between 0.2 and 19.8, okay, it means that we will not reject the hypothesis, all right? But once the value falls above 19.8, or it falls below 0.2, we are going to reject the hypothesis, all right? So once we are saying that the true population parameter will fall between 0.2 and 19.8, all right? So that means that once the value is within the range, we will not reject the hypothesis. But once the value falls outside this range, as in the black section, we are going to reject the hypothesis. Now, one thing you must know is that this 0.2 here, it corresponds with the z-value of negative 1.96. Because remember, it is the mean plus or minus here. The mean plus or minus the critical value times the standard error. So what it means is that this 0.2 here, if I compute the z-value of 0.2 as a figure, I should get negative 1.96, all right? We can test that and see. Remember, z-value is equal to the value, the x value, whatever value it is, minus the mean over standard error. And in this question, remember, the mean given is 10. The standard error is what? 5. So let's compute the z-value of this 0.2. The z-value will be 0.2 minus 10 all over 5. You get negative 1.96. Okay. Then, if you compute the z-value of this 19.8, it will be 19.8 minus 10 over 5, you get 1.96, all right? So these values here, x is 0.2 and x is 19.8. This value here, the 0.2, corresponds with a z-value of negative 1.96. And then this s value here corresponds with a z-value of what? 1.96. All right, so follow this analysis carefully. If you couldn't follow, just replay that. All right, so if you couldn't follow, just replay that part in the video. All right, replay that part of the video. Okay. Now, as I said, when it comes to critical value computation, it must be straightforward for you. All right. Critical value computation must be quite straightforward. So critical value or the z-value is the hypothesized figure minus the figure minus the hypothesized figure all over standard error. All right, that is how we compute the critical value. Okay, that is how we compute the critical value. We've done this when we are doing confidence interval, and I believe it must be quite simple for you. Now, there are three approaches in conducting hypothesis test. The first one is that computing the z-value and comparing it to the critical value, and then calculate the sample mean and compare it to the critical mean, and then computing the p-value. For me, one of the simplest approaches is the first one, that is computing the z-value and comparing it to the critical value. All right. Now, this is how we compute a z-value. So z-value is the sample mean minus the population mean all over standard error. And this computation has been done in confidence interval when I taught confidence interval. So if you don't understand it, kindly refer to the video of the confidence interval, right? Now, once we are doing hypothesis testing, we can have a one-tailed test and a two-tailed test, okay? We can have a one-tailed test and a two-tailed test. Let me give an example. Now here, if my null hypothesis is that, let me show my whiteboard. So now, if my null hypothesis is that the average is equal to 50, okay? The alternative will be that the average is not equal to 50, all right? Now, remember that